Okay, so this is where we've been living here. We've been living on this circle. Let's actually do work here. Statistics. It's today, the 6th. Okay, high success on the web work. So let's just move on. Okay, here we go. So this our journey here on the circle all started with this, right? Not that. With this. No, not that. This. Okay, which is what? Radius. We're all about the radius, right? We're all about a radius length. We're measuring everything in radius lengths. We're using radius length to measure angles. We're using radius length to measure position on the circle. So it's all about a radius length. And so what is this right here? What am I showing you here? In terms of radius lengths, what number of radius lengths am I showing you? That's just one, right? That's one radius length. And so we know that can represent what? The radius of any circle. So if it's the smallest circle you can think of, what's the radius of that circle measured in radius lengths? 1. And if it's the biggest circle you can think of, you know, a circle around the Milky Way, right? And you're going to measure the radius in the radius lengths. How many radius lengths is one radius of a circle around the Milky Way? 1, okay? So we're all about measuring. So with angles, let's go back to angles. So we took the radius length and we peeled it off and we wrapped it on the circle. And we said that defines an angle, right? We said that defines an angle. And because it defines an angle that cuts off one radius length, that angle was 1 what? Radian. Okay, so radius length is a distance measurement, right? It's either an arc length or like an x or y coordinate. Sorry, radians. I was talking while I was writing. Radians then is the measure of openness of an angle, right? We said angles measure openness. So radians are talking about how open an angle is. All right, so if we keep wrapping radii on the circle, then we get to here. And what's our angle? Our angle is the measure of the angle swept counterclockwise from 3 o'clock. Because we could define lots and lots of angles on this circle. So for what we're doing with sine and cosine, we need this particular angle. The angle swept counterclockwise from 3 o'clock. Okay, so if we go 2 radius lengths of arc length, that defines an openness of 2 radians. And then 3 is here, 4 lands here, 5 lands here, and then 6. And then we said exactly halfway around. How many radius lengths to get halfway around? Pi. And then exactly all the way around? 2 pi, obviously, right? So it's two halves of a circle. Okay, so and then we said, so this is a good starting point, 1, 2, 3, 4, 5, to see exactly what we're doing, what these numbers mean. But what's the disadvantage to these angles, 1, 2, 3, 4? What's that? Yeah, they're just in weird places, right? They're kind of not in useful places if we're thinking about symmetry, right? If we're thinking about symmetry of the circle, they're not in useful places, okay? But it's our starting point, and it keeps us remembering that angle measure is a number of radius lengths or openness in radians. Okay, so we want that. So what do we do? So we use pi then, since pi is exactly half a circle, we can use pi then to get nice symmetric places on the circle, angles that may be useful in terms of symmetry. Okay, so the first thing we do is we break up the top of the circle into four equal angles. Okay, and each of those angles would be what? How much openness for each of those? A quarter of pi, right? Not a quarter circle. It's an eighth of the circle, which would be a quarter pi of openness. Okay, so here's how we remember those angles. So you just break the circle up into 8 equal pieces, and then you just count. You count quarters of pi, so it would be, ready? 1 pi over 4. I'll get there. Let's see. It's kind of touchy. Here we go. 2 pi over 4. 3, 4, 5, 6, 7, 8. So all you have to do is count. You don't have to memorize. Just know that when you have openness of a quarter pi or 1/8 of a circle, you just count 1, 2, 3, 4, 5, 6, 7, 8, and those are your pi over 4 angles. Okay, but just as a reminder, these are not labels for places on the circle. These are actual numbers. So, for instance, 7 pi over 4. We know what? We know 4 is somewhere around here, and 5 is here, and 6 is here. So this angle 7 pi over 4, estimate it to be what? Like 5.5, right? Something like 5.5, 5 point something. So find 7 pi over 4 in your calculator. Get that number. Right? These are values. They're still values of radius lengths and still values of openness of angles. They're not labels for points on the circle. It's not that we're calling that spot 7 pi over 4. It's that it's a number. It's the number of radius lengths swept counterclockwise from the 3 o'clock position. What is it? 5.49. One more decimal place. 8? 7?
Oh, yeah, 8.
8. So 7 pi over 4 is very close to the number 5.498, which is the number of radius lengths, starting at the 3 o'clock position to get to that point on the circle. Okay, so remember that these symbols with the pi's in them are still numbers that have meaning. Okay? All right, so those are pi over 4 angles, but we already know these, right? So 2 pi over 4, 4 pi over 4, 6 pi over 4. We already had those. We know, so the top of the circle is what angle? Pi over 2. So it was 1 pi over 4, 2 pi over 4. That's pi over 2. Then 3 pi over 4, then 4 pi over 4. Pi. 5 pi over 4, 6 pi over 4. 1.5 pi, right? 7 pi over 4, then 8 pi over 4. Okay, so doing that, we get 4 new angles, right? The ones that kind of split each quadrant exactly in half. Okay, and then we can kind of do the same thing here. With 6th. So now I'm gonna break up the circle, the top of the circle, into 6 equal measures of openness. Okay, so the first angle then, so this angle right here would be 5 over 6. And just like before, we're gonna march around the circle, and you don't have to memorize. All you have to do is count. So just as long as you know that each quadrant is split up into 3 equal angle measures of openness. The half of the circle is split up into 6 equal, and the whole circle this is 12 equal angle measures. And those are pi over 6, and you just need to count. Ready, here we go. 1, 2 pi over 6, 3 pi over 6, 4, 5 pi over 6, 6, 7, 8, 9, 10, 11, 12. So all you have to do is count how many pi over 6s. Just go around the circle and count. And then again we have, so 3 pi over 6 at the top. Is it right? Same as pi over 2. We get to the halfway point. 6 pi over 6. Pi. Down here, 9 pi over 6. 3 pi over 2, or 1.5 pi. And then 12 pi over 6. 2 pi. So those, okay, so here we get now 8 more new angles. Pi over 6, 2 pi over 6, 4 pi over 6. Okay? But we notice that there are 4 of those that actually can be simplified further into thirds. Okay, so 4 of the new ones, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, we're done. Those are fully simplified. But then these ones closer to the top and bottom of the circle can be, can be simplified to thirds. So that pi over 6, the 2 pi over 6 becomes pi over 3. The 4 pi over 6, 2 pi over 3. The 8 pi over 6, 4 pi over 3. And the 10 pi over 6, 5 pi over 3. Okay, so these are the thirds. These 4 angles are the ones that are like the thirds. And then these 4 are the ones that are the sixths. And then these 4 are the ones that are the fourths. And then again, the top, we know the top and left and bottom and right side of the circle are those pi over 2 pi, 3 pi over 2, and 2 pi. So these are what we're going to call the 16 key angles, the 16 key angles on the unit circle. So how many total angles are there starting at 0 all the way to 2 pi? How many total angles are there? 16? Nope. There's as many as you want, right? There's as many as you want. So here's what students do when they get to application problems or they see a picture and they see an angle that's landing them somewhere around here in the circle. And they conclude what? It must be. Unless you know for a fact that it's pi over 3, you can't assume that. How many angles are there represented in that bubble that I just drew? How many angles are there? A lot, an infinite number of angles that are close to pi over 3. So just because you see an angle that's giving you that point on the circle or that terminal ray somewhere around there, it doesn't mean it's pi over 3 necessarily, unless you have definitive info that it is. Okay, so don't just assume that the 16 key angles are the only ones. They're just the nice symmetric angles that we like to have for applications and such, but you can't just, if you come to a situation and you see an angle, don't assume it's one of the 16 key angles. There's an infinite number of angles around the circle. So you got to know for sure that you have one of those. Okay, what do I want to do now? So we want to look at, I'm focused here, I've got on the pi over 4. So now we've got this angle pi over 4. And what does the number pi over 4 mean? What does that mean? Okay, so pi over 4 is the angle measure that is equivalent to 1/8 of a circle, right? Pi over 4 is the angle measure. And how is it that, right? So what does that, how is it that it's 1/8 of a circle? Is that just what we call that point right there, pi over 4?
It's 1/8 of number radius lengths that would needed to complete a full circle.
Which is what? 1/8 of the number of radius lengths to complete a whole circle. Just 2 pi. Which equals? Pi over 4. So it's a number. So put it in your calculator. Pi over 4. Put it in your calculator. It's going to be something like 0.77 or 0.8 or something like that. What is it? 785. 0.785 what? 0.785 what? Radians, which means 0.785? Radius lengths, right? So this is that length right there, from there to there, is pi over 4 radius lengths, or 0.785 radius lengths, okay? One more time. These are not symbols designating places on the circle. They're not names. They're numbers. They're numbers of radius lengths. Okay, so we want to now talk about sine and cosine. So here we are. We've got this angle, pi over 4. It puts us at this point in the circle. So I'm going to tell the person next to you just what is the definition of sine, what's the definition of the cosine, and then estimate for this particular angle pi over 4. So sine is what? sine of, or just in general, sine of theta. So you have to do it for your quiz. You have to write it out, and to get full credit, you need all the details. So practice. Sine theta is what? What is that? And it's not 2 words. It's a long phrase, right? Same with cosine. And then estimate using those meanings. Estimate sine of pi over 4 and cosine of pi over 4. Go. Did you raise your hand? No. Okay, tell me.
It's the vertical distance above the horizontal axis in radius length.
He says the vertical distance above the horizontal axis in radius lengths. What do you think? Okay, and so what do you estimate it for this particular angle, sine of pi over 4?
It's about 0.7.
About 0.7. You see, this is maybe a little small, but this is 0.6 here. Here's 0.8. So he's saying about 0.7. What do you think? Yeah, 0.7 of a radius length. So when you sweep an angle pi over 4 on the circle, then that puts you about 0.7 or 70% up the way of the radius length. Notice it's not a half, right? We went halfway up to the top in terms of the angle sweep, and we didn't end up with halfway up the radius. We ended up with 0.7 up the radius. Do you see that? So we split up quadrant 1 with this angle. We went half of pi over 2. But our y-coordinate was not half. Our y-coordinate was 0.7. Okay, meaning for cosine. Somebody knew meaning for cosine. Yeah?
The distance to the right of the horizontal diameter.
Distance to the right of the vertical diameter. One more detail. In radius lengths. And what do you estimate cosine of pi over 4 to be? Yeah, 0.7 as well. And so by symmetry, this kind of makes sense, right? So if we sweep an angle halfway through the first quadrant, by the symmetry of it, we would expect the sine and the cosine to be the same, and they certainly look like that. About 0.7, about 0.7. Okay, so we want to calculate them exactly. We want to know exactly what is the sine and cosine of pi over 4. Okay. Well, that's because you remembered it from something else. So I'll give you a hint. So here, take this. This represents this distance from here to here. Represents what? Sine or cosine? From there to there. That's cosine, right? Move it down here. Okay. And then this distance from here to here represents sine. And we're trying to figure out exactly what those distances are. Notice it's a right angle. Okay, so see if you can figure it out. Try to forget everything you've ever learned about trig in the past. Like if you've learned something about this, just go with what we've learned so far and my setup here, and see if you can mathematically derive it, right? So mathematically figure out what those values are. And then work together. So if you're stuck, what is it? It's the radius, but everything we're measuring is in terms of radius lengths. How many radius lengths is that? 1. From here to here is 1. From here to here is 1. From the center out to the circle in any direction is 1. So, and then what do we know about, because of the symmetry of the angle, then what about our cosine and sine? Yeah, so it's a little bit of an assumption, but it's a good assumption. We can argue by symmetry that those are going to be equal. And so our Pythagorean theorem says, so call this x. Therefore, what's the sine? Also x. They're the same, right? Pythagorean theorem says? A squared plus B squared equals C squared. So this is how we start. By symmetry, we assume that those are the same, cosine of pi over 4 and sine pi over 4, so we label them the same unknown. Call it x, call it y, whatever you want. We know that the hypotenuse is 1 because it's the radius length. And so then now we can solve for x. 2x squared equals x squared equals x equals which equals? Okay, find that number in your calculator. We're expecting it to be close to what? We're expecting it to be close to 0.7. That's what we estimated for the sine and cosine of pi over 4. So 0.2 radical 2 over 2 equals about 0.707. Let's do one more decimal place. 7071. Okay, so but no matter how many decimal places you take, it's an approximation. So how do we express it exactly? How do we express the sine and cosine of pi over 4 exactly? Radical 2 over 2. So this expression is that exact number of radius lengths that you are to the right and the exact number of radius lengths that you are up when you sweep an angle of pi over 4. So remember, input, angle swept counterclockwise from 3 o'clock. Output of cosine, horizontal distance for that point on the circle. Output for sine, vertical distance for that point on the circle. Okay, so let's do the same thing for pi over 6. So if we were to come up here and say, what are the coordinates of this point? And we want it to be universal for any circle, right? What are the coordinates of that point for any circle? X coordinate is? We just found it, radical 2 over 2, about 0.71, okay? And the y coordinate of that point? Measured in radius lengths, right? About 0.7 of a radius length. Exactly radical 2 over 2 of a radius length. Okay, so let's do... All right, here, so first, I want you to estimate the sine and cosine of pi over 6. Tell the person next to you. Estimate the cosine of the sine of pi over 6 and the cosine of pi over 6. No calculators. You're using your meanings for sine and cosine to estimate these. You just estimate. You're just looking. Is it Kevin? What's your estimate for sine of pi over 6, Kevin? What's that? Half. Right? It's coming right in here at halfway up the radius. That's right. Cosine pi over 6. Jason, what do you estimate the cosine of pi over 6 is? That's what cosine is. It's the horizontal distance to the right of the vertical diameter for this point after we sweep the angle. Yeah, so play 0.9 or 0.8. So actually, looking here at the scale, this is 0.8, this is 0.9. 0.8, 0.85. Okay? So we want to find these exactly, just like we did for pi over 4. We want to find them exactly. Now, in order to do that, I need to tell you that sine of pi over 6 is not about 0.5. It is 0.5. Exactly. And you can see it's coming in right here at 0.5, and that is absolutely true. That if you sweep an angle of pi over 6 radians, you are exactly halfway up the radius. You get exactly halfway up the radius as your y-coordinate. So now I want you to find this exactly. Go. Find exactly. Again, it's the same thing. This is not for your calculator. This is for pencil and paper. Pencil and paper. And I'm going to call on someone to get me started on this. So, should all be able to do this. Chris, did you get started on it? Tell me. How'd you start? Which is? So the hypotenuse is 1. Okay, good. What do you think? That's it. That's perfect. Keep going. One fourth. Okay, so that's 1/4, and that's 1. So then a squared equals 3/4. 1 minus 1/4 gives 3/4. So a is? Right. Square root of 3/4 is square root of 3 over 2. And we expected that value to be about 0.85. Put it in your calculator. What is radical 3 over 2 exactly? Or, I mean, a good approximation? 0.866. One more decimal place. 0. Okay, that's what we thought. We thought it was pretty close to 0.85. So exactly, so when you sweep an angle of pi over 6, the resulting point on the circle then is 0.866, or radical 3 over 2 radius length to the right of the vertical diameter. Okay, now notice, any questions about that? So notice the angle pi over 3. What do you notice about the triangle that we would make with pi over 3 relative to the triangle that we just made for pi over 6? It's the same triangle, right? It's just the legs are flipped. Do you see that? Notice what's the cosine of pi over 3 then? 0.5, just like the sine of pi over 6. And so then by symmetry, it's the same triangle, and now your y-coordinate, or your sine, is the radical 3 over 2, 0.866. Okay, so that gives us, now we just found in this first quadrant, we've got the sine and cosine of all the key angles in the first quadrant. Can I erase? Any questions? So here are those. So at pi over 6, cosine and sine, or x and y coordinate, radical 3 over 2, 1/2. And then at pi over 4, they're both radical 2 over 2. What are we talking about? Number of radius lengths to the right and up. Number of radius lengths to the right and up. Or the cosine of the angle and the sine of the angle. And then 1/2, it switches for pi over 3. And then, of course, what's the, at angle 0, what is our cosine and sine? Cosine is 1, sine is 0. Your 1 radius length to the right, your 0 radius length up, and at pi over 2, cosine is 0, or 0 radius lengths right or left, and 1 radius length up. Okay, so now by symmetry of the circle, notice that, so yeah, we found the y and x coordinates, or the cosines and sines for the angles, the key angles in the first quadrant, but then by symmetry, we just found them all just by applying the right negatives, right? Positives and negatives. So for instance, what is the cosine of 5 pi over 6? What is the cosine of 5 pi over 6? Negative radical 3 over 2. Okay, and what is the sine of 11 pi over 6? Negative 1/2. Do you see that? So this is going to have the same y coordinate as this, just the opposite. And this will have the same x coordinate as this, just the opposite. So using negatives now, we just found all the cosines and sines of all 16 key angles by applying the reference angles in the first quadrant. Okay, so I got some questions for you. Practice. Go. Talk. Talk amongst yourself. Practice with these. Let me turn on the other rectangles. So I'm just going to turn those on quick. Hold on. Okay. I want the best, most intelligent response. Who asked for that? I want a response that shows full understanding. That's what I want. Okay, here we go. Let's see how we did. What's that? Think you got it?
Got 'em all.
Got them all? All right. Let's see. So, tell me your name again. I'm just going to write down the row. Tell me your name. Yeah. Alonzo. What's the cosine of 5 pi over 6? Negative square root of 3 over 2. Agree?
Yes.
And Brandon, sine of 11 pi over 6.
Negative 1/2.
Negative 1/2. And Kenton, cosine of 5 pi over 3.
1/2.
He wants 1/2. Agree? Jimeno, sine of pi. 0. Cosine of 3 pi over 4. It's Daniel, right?
Yeah.
Okay. Negative root 2 over 2. Agree? Sine of 2 pi over 3. Let's skip and go to Colleen. I'm sorry. Was it? Bryce, sorry. Sine of 2 pi over 3. So we're going to come up here to this angle, and we want, what is sine? What's the meaning of sine? Vertical or horizontal? So we want the vertical distance for this point from the angle 2 pi over 3. Right. It's going to be the same as the vertical distance for pi over 3, right? It's going to have the same sign as pi over 3. Okay, what angle measure gives a sine of 1/2? Talia.
Pi over 6 and 5 pi.
Right. And Gary, what angle measure gives a cosine of negative 1/2? Nope. So we're going to do angles from 0 to 2 pi here. So we want a cosine of negative 1/2. So I'm going to go down 1/2 or over to the left 1/2? For cosine? Left. So here I am. What angles give me that cosine? There you go. 2 pi over 3 and 4 pi over 3. And what angle measure gives a cosine of radical 3 over 2? Ori. Was it? Pi over 6 and 11 pi over 6. Agree? Okay, so far, that was one thing I want to talk about. So far, we've only been talking about angles between 0 and 2 pi. Are there any other angles besides those? So we can go once around the circle, but then we can keep going. All right, so you can have an openness of more than one circle. All right, don't pack up. Don't pack up. You can have an openness of more than one circle. All right, so really, how many angles are there that gives us a sine of 1/2? You just keep going around and around the circle. So really what we want is pi over 6 plus, we could just keep doing a full rotation, right? So what is one full rotation of angle measure?
2 pi.
2 pi. So we could just keep adding any number of 2 pi's, right? So we can say like times 2 pi k, where k is any integer. But then also what? 5 pi over 6 plus 2 pi k. So you can do that initial angle of 5 pi 6 plus any number of full circles to take you back to that same place on the circle will give you that sine of 1/2. So if we want to express all possible angles, all infinite many of them, we need that statement right there. Pi over 6 plus any number of rotations, and 5 pi over 6 plus any number of rotations. Okay, vote for almost infinity. Yeah. What did I call it? What was the app? Llama Judge. Llama Judge.